Okay, thank you. Thanks for the introduction, Mohammed. Good morning, everyone. Welcome to my talk today. Today, I'll be talking about Sponge, a distributed system that provides fast reactive scaling for stream processing with serverless frameworks. I'm Wook Song, and I'm just on the edge of receiving my PhD degree from Seoul National University under my advisor, Byung-Gon Chun. And this is a joint work with researchers Taegeon and Sameh, professors Myeongjae and Gon from Samsung and Microsoft Research, as well as UNIST and FriendliAI. So today, a large number of data analytics jobs deal with real-time stream data, which are used in a variety of cases like real-time analytics, fraud detection, and monitoring various services like social media and the stock market. Due to its characteristics, these jobs are latency critical, as lower latency and faster execution often means more value in the processed information. In addition to low latency, it's also important to maintain high throughput as well as correctness, resource efficiency to reduce the costs for stream processing. All modern stream processing engines aim to meet this criteria while designing their systems. However, as we're dealing with real-time data in stream processing, it's often very tricky in the sense that these data are very likely to be irregular and unpredictable, as we cannot foresee upcoming events in advance. For example, we often face situations where we experience sporadic bursts of input data in terms of volume caused by random events like influencer tweets, breaking news, and natural disasters. These situations are very challenging to handle, as it requires the stream processing system to rapidly scale to meet the service level objectives for the increasing input loads. Under such circumstances, what really happens in the stream processing engine is that due to the different characteristics of different stream processing operators, some resource-intensive operators fail to provide enough throughput with its CPU resources to handle the increased input load injected to the pipeline and cause data queues to pile up and flood the memory, which eventually increases latencies for real-time analytics jobs. In these situations, existing works have been able to scale stateless operators on the right, like map and filter, by spawning more tasks that simply take and output each individual events after processing them independently. However, obviously, it's more challenging to deal with stateful operators on the left, as they keep states, which are basically aggregated data for specific partition keys, often collected by performing shuffle operations that fetch data from multiple upstream operators. Nevertheless, while stateful operators mainly suffer from resource shortages in terms of CPU and consequently memory, as shown in the slides, existing works fall short in scaling these stateful operators effectively, as it requires complicated mechanisms to guarantee correctness in the states. In our work, we aim to provide mechanisms that provide fast adaptation for scaling both stateful and stateless operators. Well, in providing enough resources for stream processing systems to keep latencies low, one obvious approach would be to simply over-provision a large amount of CPU resources to provide enough throughput for the stream processing engine, but this results in a severe amount of idle resources and extra costs, while only covering for the indicating amount of increased input loads, failing to provide a comprehensive solution for the problem. As a result, it makes more sense to provide a solution based on an on-demand resource provisioning method, which is made widely available through cloud service providers. Existing approaches mostly base their solutions on traditional virtual machine instances, which provide relatively stable and powerful performances and wide network bandwidth. However, using VMs are infeasible in our context, as it requires more than 25 seconds of startup time, which can lead to catastrophic results and cascading latencies of stream processing systems. Consequently, we propose using serverless frameworks as a solution for rapidly handling such problems, as they're designed to be flexible and short-living with fast startup times, while they exhibit limitations on weak network performances and high cost. As a result, we take the best of both worlds and aim to use the fast scalability of container-based serverless instances for short-living bursty input loads, along with the stability of VM-based instances for the long-living input loads with an automatic scaling mechanism that can rapidly offload bursty input load to serverless instances, while also reducing extra costs by keeping over-provisioned idle resources as small as possible. Nevertheless, we have a few challenges that we have to address in our solution in order to make our solution work in practice. First, serverless instances are not designed to provide stable network connections among each other. As they're designed to be fast and short-lived, it would incur extra initialization overheads to set up all the network environments between each of the instances. And due to such design choices, direct network connections are prohibited among serverless instances. And this becomes problematic when trying to offload adjacent neighboring operators together. Also, although serverless functions only take several hundred milliseconds to launch, there still are challenges in handling the runtime launch overheads for runtime environments like JVM. Also, weak network connections incur large overheads for migrating states and tasks between instances. As you can see from our measurements, showing the amount of time it requires for each of the different stages of scaling data processing systems, these initialization and migration costs are non-trivial. Sponge aims to scale the system within a 1-second target and overcomes these challenges that incur large overheads with the following design. First, Sponge is largely composed of two components, the compiler and the runtime. Specifically, the compiler first sets up the data path to enable the redirect and merge design principle, and the runtime provides fast reactive scaling with additional resources from serverless instances with simple, fast calculations. Let's go over the individual components one by one. First, Sponge prepares the data path before the actual execution to bypass direct network communications and migration overheads by inserting special operators in the pipeline during the compile time. As there are no concerns yet about runtime synchronization and the workload progress during the compilation phase, the DAG optimization only takes about 200 milliseconds, which is much shorter than dynamic optimization methods during runtime. Given an arbitrary DAG of operators, the compilation phase inserts 3 different operators. First, in order to prevent direct communications between serverless instances and provide flexible configuration of data redirection to different operators, we insert router operators before each of the operators, which manage the data flow through the VMs and the pipeline. By default, the router operators redirect all the data to the original operators. Next, as any operators, stateless or stateful, can eventually become subject to scaling on serverless instances, each operator is allocated with a corresponding transient operator, which is a clone operator with additional features to make them compatible on serverless frameworks and to be able to keep lightweight partial states. As router operators coordinate the data flow, transient operators are activated during runtime by router operators after specifying the partitions of key groups under which we redirect the events to each of the parallel tasks. By doing so, we can flexibly and rapidly control the amount of events that flows into the transient and original operators when scaling decisions are made during runtime. Also, by creating transient operators ahead of time, we can avoid the task migration overhead. Finally, we insert merge operators after each of the stateful operators to enable state merging between the partial states that are separately collected on the original and transient operators on the corresponding input data that are redirected to each of the operators. The state is built solely based on the redirected events and consequently does not require migrations on existing states, keeping transient operators lightweight. Instead of migrating states, we take the partial states built on the redirected events and merge them with the merge operator, which is built on the extracted state merging logic from the data flow application. Without these new operators, stream processing systems are only able to offload one of the neighboring operators and suffers from state migration overheads. To ensure correctness, our system provides synchronizations by injecting the control plane within the data plane, which is explained in our paper. At this stage, now that we have the data path ready, you probably might be wondering how much of the data we should be redirecting to serverless functions and how much serverless instances we should be using. In order to provide fast adaptation, we calculate the required number of additional cores based on simple calculation on profiled metrics. In choosing the amount of resources, our ultimate goal is to keep our CPU utilization between 60 and 80% to prevent bottlenecks as well as underutilization of resources. The CPU utilization is tracked by libraries like the npstat command on Linux for every second, which takes about 10 milliseconds per observation. Note that we aim to scale our system on CPU resources as memory usage only increases when the events pile up in the input queue when the CPU is bottlenecked, and we have also checked that we have enough network bandwidth in modern on-demand computing environments. Based on the observations and profile metrics, we can measure the average throughput rate per each VM core by dividing the average input rate by the number of CPU cores. With this in mind, now, in order to find our target system throughput to meet our recovery deadline, which aims to stabilize the system within the window interval of time, we estimate the amount of data piled up in the event queue by calculating the integral of the input rate subtracted by existing throughput and find our target throughput that satisfies the deadline based on the estimation. The target throughput is calculated for each of the operators, as each operator has different throughputs and suffers differently from the event bursts. Now, based on the derived target throughput and the throughput rate per each CPU core, we aim to adjust the amount of instance cores by adjusting the number of service instance cores within our cluster to meet the target throughput divided by the target 70% of the throughput rate per serverless instance core. Note that we have scaled the CPU core performances based on profile metrics to cover cases where VM and serverless cores have different computation performance, and also set our target utilization to 70% to provide a 10% safety buffer for profiling and estimation errors that can occur in real-time systems. Upon launching serverless instances, we provide further engineering efforts to prevent cold start latencies and runtime initialization overheads, which you can see in our paper. Let's see how Sponge acts as a whole system. To make use of the inserted operators, our runtime follows a number of procedures to correctly measure and estimate the amount of required resources for scaling. First, stream operators on VMs are initially scheduled in order for them to be long-running and ready to receive input events. While doing so, our runtime keeps track of real-time CPU utilization and input rates to detect bursty loads and the under and overutilization of resources. Based on the monitored metrics, we can estimate the amount of resources that we need to stabilize our system at an efficient CPU utilization. Now, with this estimation, we can adjust our key partitioning group and activate our redirect and transient operators to offload adequate portions of input data on serverless functions and merge the states back on the window boundaries. Okay, so Sponge is implemented on various open source projects, including Apache Beam, Apache Nemo as the program interface and the data processing framework, and currently supports AWS Lambda as a serverless framework with the help of Boto3 library for managing different instances. In our evaluation, we have used a cluster of 5 Amazon R5X large instances with an additional C5D at 12X large instance for data generation through Kafka. As serverless instances, we have used 1769 megabyte Amazon Lambda instances, which each provides a single full CPU core and have ensured that we avoid network bottlenecks by using a larger number of relatively small instances, which can be used together to effectively use more bandwidths. We have used the NextSmart benchmark for evaluating our workload, which provides a variety of queries composed of different numbers and types of stateless queries that capture most of the queries that we use in real-world situations. In this presentation, we focus on queries 6 and 8 as representative examples, while other results are presented in the paper. In terms of workload input, we have provided 3 different patterns in our workloads to confirm that our system works well under different input patterns under bursty, sine, and gradual increase curves. We have also varied the length and the severity of the burstiness, which we show in our later slides. On this slide, you can see the results for our representative experiments over a time period under a situation where the system faces as 5x bursty input load at a specific time through 80. On the left, our graphs represent the 99th percentile tail latencies in seconds, meaning that lower is better. And on the right, the CPU utilization are most ideal when they're kept within the 60 and 80% range. We have compared our system against 5 baselines where no scaling is performed, VM base that scales under VM initialization overheads, SF base, where serverless instances are naively used without direct communications and new operators, VM init, which presumes a perfect prediction for initialization and scales while performing state migrations, and 5, over, where we don't worry about the costs and over-provision resources to keep the task underutilized. obviously, the over-provisioned case excels in keeping the latencies low at all times. And in all of the queries, we were able to see that Sponge provides similar performances compared to the over-provisioned case, where utilizing CPU resources in a much more efficient manner. In order to see the effect of the different operators in Sponge, we have also shown the performance improvements one by one, starting from the SF baseline, by enabling each component to the system one after another. We can see that the performance gets better on Sponge RO, Sponge TO, and Sponge as we add router operators, transient operators, and merge operators one after another, as routing operators enable all operators to scale by preventing direct communication. Transient operators enable routing operators to instantly redirect data, and merge operators prevent state migration overheads. Lastly, we show the performances between the different runtime initialization methods where the details are described in the paper, which both show good performances to keep the latency low. Next, this graph shows the average peak tail latency among the different queries on different baselines. Under cases where we provide different input traffic patterns, burstiness, and bursty input durations. In all of the graphs, we can see that the performance of Sponge is better than other baselines and comparable with the over-provisioned case. We can confirm that Sponge is able to cover all the different cases of real-world environments where the input data pattern varies. One last evaluation that I would like to show is the cost analysis. We ran repetitive experiments on Sponge and on the over-provisioned case baseline on a 5x bursty load. And here we can see that if we do not over-provision enough resources proportional to the 5x burstiness, for example, if we only provision by 4 times the cluster size, the system experiences latency peaks in the system while incurring 4 times the original cost. While bursty traffics are often short-living and generally falls way under the 15% threshold shown on the right, in cases when the bursty inputs persist, for example, for like more than a minute, we also provide mechanisms that enable our system to use additional VM instances, which becomes more cost-effective. As serverless instances prevents the latency peaks caused by VM initialization methods and earns time for VMs to properly launch. As a result, we can say that Sponge is able to provide cost-effective and efficient solution for all times. And in our evaluations, Sponge only uses about 17% of the original cost used by the over-provisioned case while showing comparable performances. To conclude our work, Sponge keeps latency low upon sudden burst of input events by reducing the various launch initialization overheads and migration overheads. Sponge does this by instantaneously redirecting bursty input data to fast-starting serverless frameworks by automatically scaling system throughput to keep latencies and budget within our target with specific mechanisms to reduce the overheads. As a result, Sponge is able to reduce the 99th percentile tail latencies by 88% on average compared to VM scaling methods, and reduces cost to just 17% of the original cost compared to over-provisioning methods while providing comparable performances. And thank you. That's it for today's presentation, and I will be happy to take your questions.